Hi-oh! Here we are again. This time we're going to talk about energy, kinetic, potential, and conservation of it. In order to get there, we have to talk about what work is and why you would be doing work. I'm not talking about homework. I'm talking about the motion of things. Work is merely, it happens when you apply some force over some distance. Now there's a key understanding here. Must be in the same direction. That force must be in the same direction as the motion. Something to be aware of, because this is going to come back over and over again, is that we measure work in joules. So let's look at some examples here. We have a person in the upper left-hand corner. Notice they're pushing what looks like a television across the floor. Notice the direction that it's moving and the force applied are all in the same direction. This person is doing work against friction. The middle person, look at this, they're lifting a barrel, and again they're pulling up, and the distance it's moving is upward, so this one's working against gravity. But this other person, although his feet may be doing the work, his hands are not. His hands are pushing up as he's walking to the right. So no work is done because they're not parallel to one another. They're perpendicular. So that's a key idea. They must be parallel to each other to do work. So how fast you do that work is what we call power. And you may be familiar with power due to the idea of watts. A 60-watt light bulb. That's the rate at which that bulb is consuming the energy. In other words, work is being done in that filament. So power is the amount of work, in other words, the force times distance over time. It's the rate at which that force is applied for some distance. Note the two pictures below. Somebody's stacking bricks and someone's using a forklift. In both cases, the same amount of work is done. It's just that the forklift is going to do it faster, has a greater rate. And therefore, if you can do it faster, the same amount of work, you're more powerful. So let's do a little check here. We have ramp A and ramp B. Which would require more work to walk up? Realize those ramps are the same height that they have to climb. Right? You're lifting your body weight up. It doesn't matter how long this is. What matters is how high you have to lift yourself, and therefore, in both cases, regardless how they get there, it could be stairs, could be a ramp, they have to lift themselves to the same height, therefore they do the same amount of work. Well, what if you ran instead of walked? Again, same amount of height you have to get to, therefore it's the same amount of work. It's just that when you run, you'd have more power. So let's do some calculation. How much work is done to lift a 9,000 newtons of brick to a truck bed that's a height of 1.2 meters? Well, we know work is force times distance. The force is, by Newton's third law, if the weight is down, you must lift up, right? They're equal and opposite. 9,000, and the distance is 1.2. And of course, when you multiply that out, it's 1,000 or 10,800 joules. In the other case, we're asking for power. So it's that same stack of bricks. We know that power is the amount of work you do in a given amount of time, the rate at which the work is done, we know it takes 10,800 joules of work, and we can do it in 3,600 seconds, and therefore that comes out to 3 watts. But what if we can do that same stack in 10 seconds? A significantly less amount of time. Well, we know, again, power is the rate at which the work is done. The work was 10,800 joules, and we're doing this in 10 seconds. Divide that by 10, and you get 1,080 watts. It should make sense. This is definitely more powerful, requires a lot more energy to do it because you're doing it much quicker. So what is this energy thing I keep referring to? And why did I mention joules? Keep that in mind. Well, energy is the ability to do work. Guess what the unit that we use energy, what we measure energy in? You bet, joules. There's a relationship. If I have a box and I lift that box, energy is required to lift it. Guess what? The energy measured in joules is the same amount of work that was required to lift it. So if it takes 10 joules of work to lift it to this new height, there was 10 joules of work done. So of this energy, and the one I specifically just referred to is potential energy. It's stored. It's by virtue of its height. Again, measured in joules. PE, potential energy, and really we're talking about gravitational potential energy. We're not worried about a mechanical potential energy. Is equal to mass times the acceleration due to gravity times height. Why acceleration due to gravity? Because we're talking about height. We're working against gravity. And it may seem kind of strange that this is some really weird thing, but remember, the work required to lift something is now how much energy is stored there. So isn't mg, isn't that the weight of something, or in other words, the force? And isn't h the distance you lift it? F times d, isn't that work? So in other words, potential energy and work are very much related in that way. If it's not stored, it could be moving. And this is what we call kinetic energy. It's energy by virtue of its motion. Notice there's that squared relationship with that velocity. Again, it's energy. It's measured in joules. So what affects your kinetic energy the most? It's the velocity. It's squared. If you double that, the velocity, you have to double it and then square it. So it's 4 times. So in my example, if I fall off my roof and I hit the ground at 20 meters per second, so I was going at 20 meters per second when I hit the ground, how much more kinetic energy would be if I was going 80? Well, how many times greater is my velocity? It's 4 times. But remember, kinetic energy is equal to 1/2 mv squared. That is 4 times, but I have to square that. So it would be 16 times more kinetic energy. A little bit of velocity difference makes a huge difference in the amount of energy. Let's stop there.